We live in a world increasingly dominated by voice. Virtual assistants like Siri, Alexa, and Google Assistant have become ubiquitous, responding to our queries, controlling our smart homes, and even telling us jokes. This revolution in human-computer interaction is powered by the remarkable technology of automatic speech recognition, more commonly known as speech recognition. Speech recognition is the technology that allows computers to understand human speech and convert it into text. This may seem like a simple task, but it requires sophisticated algorithms to process the complexities of human language. The nuances of pronunciation, intonation, and regional accents all contribute to the challenge. The impact of speech recognition extends far beyond voice assistants. It is transforming industries from healthcare to education, making technology more accessible and efficient. Doctors use it to dictate medical notes, students use it to transcribe lectures, and businesses use it to power customer service chatbots. As speech recognition technology continues to advance, its potential applications are limitless. Imagine a world where you can control any device with your voice, where language barriers are a thing of the past, and where personalized learning experiences are available to everyone. This is the future that speech recognition is helping to create. Speech recognition is the process of converting spoken language into written text. It is a complex task that involves multiple steps, each of which requires sophisticated algorithms. The goal of speech recognition is to accurately transcribe human speech, even in the presence of noise and other acoustic variability. The field of speech recognition has a rich history dating back to the early 20th century. Early attempts at speech recognition relied on simple acoustic phonetic methods which attempted to match individual sounds to their corresponding letters. However, these methods proved to be limited in their accuracy. The development of statistical modeling techniques in the 1970s and 80s revolutionized the field of speech recognition. Hidden Markov models emerged as a powerful tool for modeling the temporal structure of speech. HMMs allowed researchers to train acoustic models that could recognize phonemes, the basic units of sound in language. The advent of deep learning in the 21st century has further advanced the field of speech recognition. Deep neural networks have surpassed the capabilities of HMMs, leading to significant improvements in accuracy. DNNs are able to learn complex representations of speech, capturing subtle variations in pronunciation and intonation. The first step in speech recognition is to capture the spoken audio signal. This is typically done using a microphone, which converts the sound waves into an electrical signal. The electrical signal is then converted into a digital format that can be processed by a computer. The quality of the audio input is crucial for accurate speech recognition. Background noise, microphone quality, and speaker characteristics can all affect the performance of speech recognition systems. To mitigate these issues, various techniques are employed, such as noise reduction and microphone array processing. Once the audio signal has been digitized, it undergoes a process called preprocessing. This step aims to remove any unwanted noise or distortions from the signal, making it easier for the subsequent stages to extract meaningful information. Common preprocessing techniques include noise reduction, echo cancellation, and voice activity detection. After preprocessing, the audio signal is divided into short segments called frames. Each frame typically represents a few milliseconds of speech. This segmentation allows the system to analyze the acoustic characteristics of the speech signal over time. The frame rate, or the number of frames per second, is an important parameter that affects the accuracy and computational complexity of the system. Section 4, cleaning up the signal, pre-processing audio. Before the captured audio can be analyzed for speech recognition, it needs to be cleaned up and prepared. This step, known as pre-processing, is crucial for improving the accuracy of the recognition process. One of the main tasks in pre-processing is noise reduction. Real-world audio is often contaminated with background noise from various sources, such as traffic, machinery, or other speakers. These noises interfere with the speech signal and make it harder for the system to identify the spoken words. Noise reduction algorithms aim to suppress or remove these unwanted sounds while preserving the integrity of the speech signal. Another important pre-processing step is echo cancellation. Echoes occur when the sound waves from the speaker bounce off surfaces in the environment and are picked up by the microphone. This creates a delayed version of the original signal, which can confuse the speech recognition system. Echo cancellation techniques identify and remove these echoes, improving the clarity of the speech signal. Voice activity detection is another crucial pre-processing step. It involves identifying the portions of the audio signal that contain speech as opposed to silence or background noise. This is important because processing only the speech segments reduces the computational load and improves the overall efficiency of the system. Voice activity detection algorithms typically analyze the energy or amplitude of the signal to distinguish between speech and non-speech segments. By applying these pre-processing techniques, the quality of the audio signal is significantly enhanced, making it easier for the subsequent stages of speech recognition to accurately extract the spoken words. Section 5. Finding the building blocks, feature extraction. After pre-processing, the cleaned audio signal undergoes feature extraction, a crucial step that transforms the raw audio data into a more compact and informative representation. The goal of feature extraction is to capture the acoustic characteristics of speech that are relevant for distinguishing different sounds and words. One widely used feature extraction technique is mel-frequency cepstral coefficients, or MFCCs. MFCCs are based on the human auditory system's perception of sound. They mimic how our ears perceive different frequencies, emphasizing the frequency bands that are most important for speech perception. To compute MFCCs, the audio signal is first divided into short frames, and for each frame, a mathematical operation called the Fourier transform is applied. This transform converts the time domain signal into the frequency domain, showing the different frequencies present in that frame. The frequency spectrum is then passed through a set of filters called Mel filter banks, which are spaced according to the Mel scale, a perceptual scale of pitches judged by listeners to be equal in distance from one another. The energy in each Mel filter bank is calculated, and the logarithm of these energies is taken. Finally, a discrete cosine transform, or DCT, is applied to the log energies, resulting in a set of MFCCs for each frame. MFCCs have proven to be highly effective in capturing the important phonetic information in speech signals. They are widely used in various speech processing applications, including speech recognition, speaker identification, and emotion recognition. Section 6. Matching sounds to words, acoustic modeling. Acoustic modeling is a critical component of speech recognition, bridging the gap between the acoustic features extracted from the speech signal and the linguistic units, such as words or subword units that make up the recognized text. The acoustic model learns the relationship between the acoustic features, like MFCCs, and the corresponding phonetic units of speech. This learning process involves training a statistical model on a massive data set of labeled speech data, where the acoustic features are paired with their correct phonetic transcriptions. Hidden Markov models, or HMMs, have been the dominant approach for acoustic modeling for several decades. HMMs are statistical models that represent a system as a sequence of hidden states, each associated with a probability distribution over the observed features. In the context of speech recognition, the hidden states correspond to the phonetic units of speech, and the observed features are the acoustic features extracted from the signal. The HMM is trained to learn the transition probabilities between different phonetic states, which represent the likelihood of one phoneme following another in a particular language. It also learns the observation probabilities, which represent the likelihood of observing a specific set of acoustic features given a particular phonetic state. During recognition, the HMM takes the sequence of acoustic features extracted from the input speech and finds the most likely sequence of phonetic states that generated those features. This sequence of phonetic states is then mapped to a sequence of words using a pronunciation dictionary or lexicon.